To perform image analysis, it's necessary that the features of interest are captured so that the measurements are performed on images that are not pixelated. Does any of you have an old cathode ray television that you have seen in your houses, old CRT television? And when the cathode ray tube starts to die off, you will see squares in your TV. Those are the pixels, and you can tell the TV manufacturer exactly what their resolution was if you measure the pixel size, right? Do you want those pixelations? No, you don't want the pixelations. Therefore, you want to have the images captured in such a way that they are not pixelated. Nowadays, if young kids here will not even know what pixelations are, because the new cameras are so good that you will not get pixelation unless you go into extremely high magnifications. So you don't want pixelations. A round object, when pixelated, will have jagged edges, right? Because every TV, if you look at it, it's all based on square pixels. So basically, if I have a circle, the perimeter of a circle is made of lines, right? So basically, but you have so refined, so small lines that you will look like a circle. If you have pixelations in your TV, you will know that. So look at some old cathode ray tube TVs that you will know what pixelation is. Okay, I'll skip some of these things. I think you don't need that. I'll explain when we have. So image processing, it's a tool for microstructure quantification. There are several steps involved in the process. We can do a lot of different things. Okay, so simple idea for pore structure quantification. If I have a 2D image, and I'll talk about stereology in a while. If I have a 2D image, and all I am worried about is the porosity, what is the color I am looking at? Black, right? Now, anytime you do an image analysis, your image processing software, unless you have an advanced image analysis software like Aviso, it doesn't like to do color images. You do grayscales. How many intensities in a grayscale? 256, right? So you have 0 to 255. So total 200, 0 is black, and 255 is the white. Yeah, 255 is a white, and in between all the grayscales. So 0 to 255 is what you look at, and here I have shown a color picture. But if you can make the software pick all the pixels with, say, 220 to 250, and you can adjust the scale in that. Roughly 220 to 250, they will be very bright. If you make them pick all between, say, 0 and 10, it will be very black, right? So, and if you say that, here is my square area, or whatever is the area, pick all these pixels with grayscale value less than 10, find out the area of all this pixel, divide it by total area, what am I getting? The area fraction of how much pores I have, right? Get it? Now, that's just one 2D. What is basically 3 dimensions? A stack of 2D is 3D, right? If I take hundreds of images and lay one on top of the other smartly, I can get a 3D. So basically, if I do a number of 2D analysis and do some statistical operation on that, will I not get the total porosity? Will I not get the total amount of fly ash? Will I not get the total amount of CSH? You can do whatever you want. That's simple idea of image analysis. Now, how many images can you sit and scan? So you have to find out some smart ways of overcoming that. Some of my slides have been messed up from, maybe it's a version of the computer, I think, because some of these pictures are hiding the text. Maybe it's a version of the one that you have. Well, I don't know what I have. It's a new laptop, so the university, they recently installed something. They probably did Office 10. That's what you have also, right? Okay, maybe that's different. Okay, so here is a microstructure of a cement paste that you've seen. What is A? No, what is A? What is it likely to be? This is the hydrated cement, so could be the CSH around unhydrated cement. What is B? Where is B? I think this is B. What is B? A void. What is C? Unhydrated cement. What is D? All are hydration products, right? So again, you're comfortable with this idea. This is just a plain cement paste. Now this is a paste. I showed you this left picture. This is a 0.45 water cement ratio paste, 100 days. 0.3 water cement ratio paste, 100 days old. Which one will have a higher strength? 0.3. Which one will have a higher durability? 0.3. Which one will have a higher degree of hydration? 0.45. Right? Because 0.45 had more water. You can see that you have a lot of unhydrated cement left here. Do you have as much unhydrated cement here? No. So degree of hydration is higher here, but the properties are going to be better here. It's a simple idea to let you know that degree of hydration cannot be used as a measure of performance. A lot of people do that. I have 90% degree of hydration. So what? You've put in a lorry load of water and therefore you have 90% degree of hydration. You have bad concrete. So degree of hydration is never ever a measure of property. It is just a tool for you to find out how much cement is hydrated. That's it. It has no relation with property. Some people plot degree of hydration versus strength. Please don't do it. Okay? That is, degree of hydration and strength have absolutely no relationship unless every other parameter that you have done is constant. Okay? So generally when you compare specimens, never do that. So you see a lot of unhydrated cement, and then the same idea of core shell, hard core, soft shell. The harder core is much more in this than the harder core here. Therefore, this will be stronger and stiffer. Right? This will have a higher strength, higher elastic modulus. This will have a lower strength and lower elastic modulus. Simple ideas. So now, just to show you some ideas of segmentation, I'll skip this picture. I'll do feature quantification. So if you get an image like this, you can use, let me do this thing first. I'll show you that. Okay. Have any of you used this software? If not, I'll give you this link, free to download. Very, very powerful software. None of you will have to buy any expensive image analysis software ever. This has so many add-ons. You give it to a student if you are a faculty. Ask them to work on this, find out what the different options are, give them some images to play around. Very simple interface. It is from the National Institutes of Health in the United States. So this is basically done for medical imaging. They did it to do scans and MRIs and all of that. So it's very powerful also. Okay? And it's freely available in the web. You can download this free. It has a very long documentation. It has a lot of plugins that you can add on to. You can do plenty of image analysis with this, and pretty much you wouldn't have to buy an image analysis software for any of those purposes. And then I have a lot of links on how to use ImageJ, lot of simple links on how to do this also here, so that you can use it. Okay. Let me go back to. So, if I get an image, so basically what I have done this is clean this image just to give me the two contrasting faces. The black is what? Voids, and the white is the solid. Now I'll give you some theory of some very interesting techniques. And if you have a student that's interested in writing programs, if you are interested in coding and writing programs, you can make all these wonderful programs quickly, save it for yourselves, work on it. And that's another thing that I'll encourage you guys if you are in the academia. Start writing small programs for different things and keep collecting it in whatever language you like. C++, MATLAB. Most institutions these days, I was talking to different people, all of them have MATLAB. Free MATLAB in all institutions. C++, MATLAB. Use any of those tools if you're interested. And many of the kids in these days know programming to a certain extent. Have them program different things and have yourself a library of these things so that you're not searching for a software when you need them all the time. Right? You're spending time, what software will. And so the reason I'm saying is, a lot of people keep asking me what software will do it. You need only 4 lines of MATLAB code for many of these things. Very simple. MATLAB has an inbuilt image library. MATLAB is so powerful. that it has an inbuilt image library. It can do it can do a lot of things that ImageJ does, but ImageJ does it in a more involved process. MATLAB, the background, you don't know what it is doing. Sometimes you will get a little upset if you don't know what it is doing. It spits out an answer, you don't know really if it's done it the right way. But ImageJ will give you every step. So write some programs if you're interested in that, so that you can keep it as your own resource. You don't have to rely on anybody else. Okay, so this is called stereology. The idea that if I get a 2D image, I can extrapolate it to 3D is simply called stereology. Okay, so have you seen the aerial maps of a place that a plane goes and takes, and then they do some manipulations to project the mountains, to depress the valleys? That is stereology. You do a 2D image and you create 3D quantifications out of it. It's called stereology. Okay, so it's an advanced field of mathematics. A lot of mathematical equations, but I'll show you just a simple one. One simple method. So here, this is one simple method of, okay, now I want to find out what is the porosity in this sample, right? Very complicated areas. How do I find the area of this complicated shape? Very difficult, right? Is there a way to find the area of this complicated shape? Is there an equation for that area? No. So one of the ways the software does it, it draws a lot of lines this way. You see here? It draws a lot of lines this way, and then wherever there is no black area, it cuts off the line. So here the lines are only where there is black areas. And then what it does is, it adds up the length of all these lines that you see here, divide by the total length of all these lines. You see, you get a good estimate of what the porosity is, right? And I'll tell you more advanced mathematical tools. I'll show you simply to give you a feel for this. You get this idea? Very smart idea, right? Because you can't get any other shape, you can do it this way. So that's called the line fraction method. Now many of these tools now can actually draw a line around it, calculate how many pixels are in those, and then divide the number of pixels inside this by total number of pixels. That also will give you the area fraction. Area fraction of pores in 2D, if I have enough number of that in the z direction, can I average them in some statistical manner to find out the 3D representation, and that will be my porosity. So this is one simple way of doing it in image analysis. So now there's a lot of times, so I saw some people doing pervious concrete stuff here. For pervious concrete, if you want to find the porosity, a lot of times how do you do the porosity? You tape the whole thing around, or you put it inside an envelope, you seal the sides, you add water, find out exactly how much water you have added. By the time you're adding water through the top, some of them are spilling through the sides. You don't know how much you're adding because your sleeve is not tight and something is leaking through. And 5 times you do 5 samples, it's giving you 5 different values with a standard deviation of 100%. You don't know what to do, so you now then say, hey, this is standard experimental process, right? I don't like this result. Remove that sample. I don't like this one. Remove that sample. I take only what pick and choose, right? So again, that's another thing that you're not buying things from a supermarket in research. If you're doing experiments, you can't pick and choose what you like. Okay? Statistically, if you're doing it statistically, you have to do it the right way. That's why sample size is important. Standard deviations are important. You can't say, I don't like that sample. If you have real reason not to like that sample, when you know that I made that sample poorly, it's not correct, yes, ignore it. But you can't randomly ignore. Yeah, I tested the strength. I was expecting 45. I got only 35. Therefore, I removed it. You can't pick and choose like that. That is not the right way of doing research. You have to, and that's why I said plan your experiments. Do it well so that you don't have to go back and look at and scratch your head and see how many data points I have to delete. Right? Oh, my professor told me that strength porosity relationship is exponential. If I remove these 4 points, it will become exponential. Therefore, I remove those 4 points. Right? I've heard enough of this. That's not the way to do research. You should ask the other way, why am I not getting this exponential relationship? What did I do wrong not to get it? And then be prepared to go to the lab once more, mix some more, wait for another 28 days, and get results. Get the right results, right? Okay. So that's the line fraction and area fraction. You can do cumulative frequency histograms to find out equivalent pore sizes. All these pores you can probably consider them to have some kind of an equivalent size, and you can do histograms so you can know which size is large. Image J that I told you about, resources. Okay, sizing the image, so you have to crop the image, you have to make sure that the image has the right size that you need. You have to have a representative size. So if you have a big fly ash particle here, like this becomes a non-representative image, right? So the size of any feature in your image should be less than 10 to 15 times the size of the image, as a rule of thumb. Because if you have a big fly ash here, then I will say that I have 50% of fly ash in this image. In your real concrete, you may have only 10% of fly ash. Just because you took that place with fly ash, you're making a mistake, right? So your representative, again, selection of image becomes important. So you cannot do image analysis on a 30,000 zoom SEM and try to quantify. If you zoom to 30,000, your only intention is to find out what that is, not how much there is. You should do this on low magnification images so that you get a representative area. So if your cement grain is maximum 50 micron in size, you have to have at least 500 microns image to do any analysis. Otherwise, you're not doing the right analysis. If in that 500 micron image, one accidental 100 micron particle came in, throw out that image. You cannot use that. Okay? Clean, crop the image, and then thresholding the image. And if you read the image manual, it will tell you exactly how to threshold the image. So basically what I have done is, and there are so many options to fill holes, lot of different things. But again, remember this, first step is to define those features that you wish to analyze so that the program can know what data is significant, which means you have to know what you have to analyze. Like I said, garbage in, bigger garbage out. You have to know what you want, and then correspondingly you can use that. So here's an image, and then I have thresholded it just by setting a grayscale of close to 0. Maybe 0 to 10, 15 maybe. Again, you have to play around with to find out what that value is that you would want. And once I threshold it, what do I have now? Pores and everything else. Pores and solids, right? The white is a solid, black is a pore. Now I can do all the image. So this is a pervious concrete sample. You threshold it. Your image analysis will tell you some kind of a right range of thresholding. You will get this black. You can clean it by filling, and then you can do all kinds of analysis on that. So stereology is basically you measure the different characteristics of the microstructure, get 3D data available from 2D data. Line and point, things that I told you before, so we'll skip that. Volume fraction counting. Have you done, I don't think you do it in India, but has anybody done air void analysis in concrete? Have you done anything called any microscope, plain optical microscope based quantifications in concrete? No. Okay, so in the US we typically routinely do air void analysis because air voids are important for freeze thaw protection. We have freezing and thawing everywhere or most places. So a plain polished section will be looked under a microscope, and it used to be a very tedious technique. Now it's all automated. While I was a grad student, this was a very tedious technique. So you have this piece of concrete sitting on XY stage in a microscope table. You look through this microscope. So you take the sample and then you put it under the microscope. The microscope is all gridded. Grids in X and Y direction. And then you move. So you turn the knob of the table so it moves one step in the X direction. And then once you've done the all, you do one step in the Y direction so it will come to the next line. Like the line analysis I showed you earlier. So you go one step, and then on my left hand, this is like a very sensitive operator here. So on my left hand I have a counter with 3 buttons. On my right hand I am moving in the X and Y direction. And with this now I am looking into the microscope. Okay, so I turn one step. If the crosshairs fall on a pore, I press the pore button. It counts the pore. If the crosshairs fall on the paste, I press the paste button. If the crosshairs fall on the aggregate, I press the aggregate button. And if the crosshairs fall on the boundary, I make a judgment on whether I can call it a pore, call it an aggregate, call it a paste. I'll do it first few times, it will be correct, and after that you will get fatigued, and whichever finger is close to it, you press that. Right? So you do this and it will take 3 or 4 hours to do one sample. It used to be very tedious. So to minimize error, we'll have at least 2 people do it and compare results so that they are correct. Very tedious process. So that was a counting process which is very similar to this. You see those points there? Basically, it's a point counting method. So I go look through the microscope. If I see a pore,